Morning everybody, welcome to this session. So last time I took a session on marketing 101 for engineers almost 2 months ago. That is more about soft skills for engineers, right? Today's session is about RISC-V, right? This will be a little bit more technical, right? And I'm going to cover 3 major aspects. First, what is RISC-V, right? We'll get into a little bit of a technical thing on what is RISC-V. Then the second question is, why is it important? Why should you care about it, right? So we'll cover both these aspects, right? So let's start with what is RISC-V. So first of all, it's pronounced RISC-V, right? A V symbol, it's a Roman V, so it's number 5, RISC-V. We'll get into history of what are the RISC 1 to 4, right? So this is an open instruction set architecture, right? That is based on RISC principles, right? Reduced instruction set architecture, computer principles, right? So there are 3 major things in here. First, open, right? What is open and why it is important. Before that, ISA ante enti, RISC-V ante enti, ee rendu manam first ardham cheskovali, right? So we'll spend a little bit of time on that and then we'll get into it, right? And then this RISC-V specific effort was started around 2010 in University of California at Berkeley. That's where actually a lot of the RISC-V work happened. And then it was transferred to a foundation. So now it's a foundation based in Switzerland. So it's an open standard that anybody can design to, right? And that's the reason it's it got a lot of momentum. So let's get to the first thing on what is ISA, instruction set architecture. So if you see the picture, right, at the very bottom level, right, since most of you are VLSI engineers or general engineering lobe, so I'll get a little bit into the entire stack, right, of what happens from the very bottom to the top. So at the very bottom in the chips you have transistors, right, and those transistors are put together for logic gates, AND gates, OR gates, avani. Gates use cheskuni, right, you get a microarchitecture, right? This is arithmetic logic units that arithmetic logic units, right? Then after that, so there is that boundary, right? You have this logical units in the chip. How are all those logical units used is the boundary between the software and the hardware. So that's where the instruction set architecture comes into the picture. On top of that, you have the machine code, assembly language, low level language, high level language. And nowadays you have the large language models and agentic AI. I mean, this will evolve, right? Paina evolve avuthundi, but the bottom, right, you have basic logic gates and arithmetic logic units in the chip. Whatever you do in the top, meer a level lo rasina sare programs, so ultimately all of that gets reduced to a set of instructions that needs to be executed in the chip, right? So that's what the instruction set architecture is. It's fundamentally an interface between the bottom hardware and all the top level software, right? That's the first thing. So it's essentially a set of commands, right, and that tells the processor how to run these operations, and then how to run those operations, right? So it's early operations, add, subtract, divide, multiply. Basically, manam paina em rasina sare, all that gets reduced to those basic operations, and also how do you fetch from the memory, right? So let's get that into a little bit, because that's where the difference is between RISC and CISC, right? So we'll take a simple example of I want to add 2 numbers, right? Generally manaki ippuda left side diagram chuste meeru, this is the basic computer architecture, right? A green portion is the memory. You load everything into the memory first, right? And then when you run the program, you fetch things from the memory into the registers on the chip, right? The memory generally is external, right, whether it's DRAM or any other memory, and then you fetch the data from that memory into the registers on the chip, and then the arithmetic logic units, which are all these operations, add, subtract, multiply, any of those things, shifting, these instructions are registers nunchi read chesi execute chestayi, right? This is the basic, at the very, I'm simplifying things a little bit, but this is a very basic picture of the computer architecture. Right. Now, with that, right, what's the difference between this RISC and CISC? And we'll take this example where you have two memory locations. I'm calling it 1600 and 1601. From those two memory locations, you want to fetch two numbers, and then you want to add those two numbers and put it back into 1600. So this is the operation you want to do, basically addition of two numbers. In the CISC, right, you essentially have one instruction which says add 1600, 1601, and all the complexity of fetching the numbers, adding them, and putting it back there, it's all built into the instruction. The software doesn't need to know any of the details, right? It's all built into the chip, right? So you just run that instruction and everything is done. So the same thing, if you see on the RISC side, if you see the right side table, right, you essentially need to do it in 4 instructions. You load it first, load both the numbers, and you do a add instruction, and then you store it back, right? So if you see the amount of time it takes to execute these instructions, right, essentially the CPU runs on clocks, right? Every clock cycle something is happening. So if you see the CISC, right, that add 1600, 1601, it will take multiple clock cycles depending on how fast your chip is running, depending on your architecture, anywhere from 4 to 6 cycles. On the RISC side, each instruction takes only 1 cycle. That's a simplification, right? So and then you have to run these 4 instructions to accomplish what the CISC is doing one instruction. So that's the fundamental difference, where instructions are sort of very loaded on the CISC side, but on the RISC side they are very simple, right? And then each one takes only 1 cycle, and then whatever you need you use to accomplish what you need to accomplish. In this case, you want to add 2 numbers, so you need 4 instructions, right? So what this means is at a compiler level, right, if you are writing software, right, CISC key compiler is very simple, right, or simpler, let me put it this way, where you just run this, execute this instruction, and you get the result. You don't need to worry about what is happening inside the chip. But on the RISC side, you have to do 4 instructions, so the work on the compiler is more, right? Essentially the fundamental difference is there is more work for the software on the RISC side and less work for the software on the CISC side. And the last thing I have on the foil, this is important to understand, is the memory to memory operations on the CISC side and the register operations, right? Because ultimately we'll get into the history a little bit in the next 2 foils, right, of why, because CISC came first and then the RISC came later. And why did RISC come later? Ante this memory used to be very expensive. If you see the evolution of computers from 1940s to where we are, actually memory was slower and more expensive. So when the computers evolved until 1960s and 1970s, then at University of Berkeley the professor started looking into these things and saying, hey, there's a lot of instructions that are not getting executed, right? There's only a small subset that are getting used most of the time. Why don't we simplify these instructions and then have more of it on the chip? When I say on the chip, on the registers on the chip, so that we run more instructions, but we run them faster and we run them on the chip. So overall the execution is faster. So that was the thought process, right? So that's where the C and R comes from, right? C is the complex and R is the RISC, right? Reduced instruction set. Now let's get a little bit into the history of how this came about, right? If you go back to actually 1940s, right? Right now, nowadays, over the last 40 years, Intel was the key company on the microarchitecture and microcomputer side. But before that, from 1940s to until 1970s, IBM was the #1 company in the world supplying computers. And there was no personal computer per se in those days. They supplied computers mostly to businesses to do their their applications, business applications. And when actually IBM started in the 1950s, they had a lot of other businesses. This was just a small business for them. And as you can see the quote on the foil, right? Then chairman of IBM was estimating around market for 5 computers, right? We've come a long way since then, right? So then, computers were very primitive back then, and instruction set, right, as in having all this set of commands, sort of began in the 1960s, right? IBM 360 was the first computer which had a set of instructions in 1964. But there was no software stack on top of it, you just run these instructions. Then what happened was, these computers were really big, the microprocessor revolution started, right? There were other companies doing what I call microprocessors at that time, but Intel, started this effort in 1971 with their first microprocessor called Intel 4004, and that was used in a calculator. So when you use a chip in the calculator, there is no software, it's just small operations. So you really don't need an instruction set architecture per se, right? So there was not much to do on the instruction set architecture side. Then Intel did their next version of it in 72 called Intel 8008. This is also used mostly in the embedded devices, right? So there is not a whole host of software on top of what you're doing. Just like in a computer, the embedded devices are for a very specific function, and then you have a small software program which runs it, right? So దీంట్లో కూడా పెద్దగా you don't have to do a lot of software, right? Then in 1978, right, Intel came up with the Intel 8086, and that's when the real instruction set architecture sort of really took off, right? By the way, there were other companies like Motorola had 68000, and Zilog was a very popular company at that time called Z8000. So there were other companies doing the things, but right, what happened was IBM, which was doing industrial computers until then, wanted to do a personal computer. So that's where this PC came about, right? Personal computer. So they looked at a lot of chips, and then they selected Intel 8086, and then they selected this Microsoft Windows, right? And then what happened was the combination of these two things, right, really took off. IBM never thought that the PC would become this popular, right? So they put those two together and then enabled an ecosystem of a lot of applications, right? So that's where it's not just the instruction set architecture or some technical superiority that you have, it's the ecosystem on top of your instructions architecture that gives you the strength to the instructions architecture. So when IBM did this thing with Intel x86 and then the Windows, all the applications got built, so they were tied to that architecture. So that's where Intel got this advantage to this x86 architecture, right? The funny thing is, this 8086, Intel had some other effort going on, as this 8086 was done in a matter of around 6 weeks, right? They had a much bigger architecture they planned, and then IBM said, I want to put out this product next year, I need something fast. So they developed this as a stopgap measure. So it's not some technical superiority which always wins, it's also the time to market, right? So they had something ready which IBM felt comfortable taking to market, which other guys didn't have, right? Then actually there were a lot more RISC chips at that point of time. So IBM had their own thing, and there were a lot of companies, DEC Alpha, VAX, PowerPC, PA RISC. Then the most important one we'll talk about is RISC at Berkeley, right? So at University of Berkeley, they had a effort, and that's what led to RISC-V. So let's go to that, right? So before going to that, right, essentially as a result of this PC revolution, the x86, Intel x86 became the de facto CISC architecture, and ARM, we'll talk about a little bit later, ARM became the de facto RISC architecture, right? But the key thing is both of them are closed, right? From a developer perspective, right, these are all both proprietary architectures. Intel control the x86 architecture, and ARM control the their architecture, which is RISC. So they are both closed, right? For a general developer out there, right, they will give you a set and you just execute and write programs to that set. If you had new ideas of, hey, I want to add these new instructions, or I have this new way of doing things, you can't extend it because they controlled it. and then that's where the open part is important. We'll get to. Okay. Guys, anytime you have any questions, please call in. Right. Okay. Now let's go to Berkeley. Right. What is happening at Berkeley, University of Berkeley? Right. So University of Berkeley a project was kicked off in 1980. This was funded by the Defense Research Agency in US. It's one of two projects actually. Stanford was the other project. They started this, so Professor Patterson at that point of time, he was working in multiple companies, and he was looking at all these different architectures, right? The IBM architecture and other architectures that were developed since the 60s. And then he was also looking at the Intel x86 architecture and other architectures. And then, one of the key things he focused on is that when the x86 has a lot of instructions, right? But he said very few instructions are getting executed, right? So we don't need all these complicated instructions. We can reduce it to a small set, which is easier to handle. So why don't we go that route, right? So that's what led to their effort, right? So actually, until then, there was no term called CISC or RISC. He wanted to differentiate what he was doing from what was happening on the x86 side. So he called his project RISC, Reduced Instruction Set Computer, and then to differentiate it from x86, he called x86 complex, right? Complex instruction set computer. So that's how RISC and CISC came about in 1981. Before, just used to refer architectures by their name. So they started in 81, and then in 81 and 82, you see those two pictures, right? Those are the pictures of the actual chips that they did. So one key thing to highlight in this RISC-V, if you see this part that I am using my mouse to show, these are all the registers. Right? Generally, you don't have this many registers on a normal chip, like say Intel chip. But the whole point of this effort, the RISC effort, is I'll have lot less instructions, but I'll have a lot more registers so that I'll get the data and have it on the chip, right? And then execute it so that I execute more instructions, but they don't have to go to memory and fetch those instructions. They're all local so that they'll run faster, so that the overall execution time for the program, when you run the entire program, is a lot faster. So that was the idea anyway. So actually, when they got the chip back, the very first one, the speed up was not as fast as they had expected, right? I mean, they had theoretical calculations of, hey, compared to other architectures, we can run this X faster. It was not that fast. But then again, anyway, whenever you do something, right, the first attempt may not give you all the results. So they kept at it, and then they did RISC-II, RISC-III, and RISC-IV, right, over the next 4 or 5 years, right. And then at the same time, right, Stanford was also doing work, right. So out of all these efforts at Stanford and Berkeley, right, these 81 to 88, there were two major companies that came out of it, right. One is Sun Microsystems. You don't see too many of those workstations from Sun Microsystems nowadays, but in the 90s and even in 2000s, the Sun Microsystems were extremely popular, right. They were really well designed, and they ran very fast. And then the other big company that came out of all this effort at Berkeley and Stanford was ARM, right. So ARM was a small company. It's called actually Acorn Computers in UK, and then they looked at all this effort at Berkeley, and then they said, okay, we'll start a new company called Acorn RISC Machine, and that became ARM, right. So these are two big efforts that came out of those things, right. So just remember that. Then okay, so this is a RISC-I to RISC-IV, which happened until 81 to 88. Then let's get to RISC-V, right. So there was a long gap after 88, right. Then in 2010, right, Professor Patterson was still there at University of Berkeley, and then there was a new professor called Professor Christie. He wanted to continue that RISC work, and then since there were already 4 projects that were done, he started a new project. We called it RISC-V, right, the Roman numeral 5, right. So this was actually, ironically, he did this as part of their, they had a parallel computing lab. This work was funded by Intel and Microsoft, right. So Intel, which was which owned the x86 proprietary architecture, and Microsoft, which owned the proprietary Windows operating system, were funding this effort, out of which came the open source instruction set architecture, right. So Professor Christie and Patterson started this work, couple of the students, and then they published their first the architecture spec, right, and they called it instruction set should be free, right, in around 2014, right. And then that took off. Again, RISC-V is not some brand new thing that they have invented or some radical new way of doing things. It's about sort of consolidating all the work that has been done since 81 at Berkeley, right, and then they put out together into one spec, right. So it's sort of an incremental effort of all those years, right. But what they did was they put in considerable effort to actually popularize this. Again, the strength of any architecture is not technical per se, right. If you see between the CISC and RISC and other architectures, they can have a lot of arguments about which one is better, right. But generally in the market, right, what wins is whichever one has more support from the developer community, right. That's the reason x86 won, not because it was technically better. I'm sure there are some technically better features, but not because it was way superior, but because it had a lot of developer support, right. When you have the Microsoft and x86, Windows and x86 together, a big ecosystem was built on top of it, right. So what these guys did in 2014 is they spent a lot of time, all over the world, right, and then a lot of people started adopting. Right. So there were 2 workshops that were held in 2015, right, and then finally they established a foundation, the RISC-V Foundation, in 2015, and that was a major milestone, because until you have sort of a structure where other people feel comfortable, right, because to be frank, this was done in the US, and the US government controls technology to a certain extent. So people really wanted this entire spec to be part of a foundation that can be outside of the politics. So they put that in that foundation, and then it took off, right. People all over the world started adopting. Right. And IIT Madras is one of the, they had 36 founding members in that foundation, and IIT Madras is one of the 36 founding members. Right. Generally, our institutes and Indian institutes and Indian universities have not been founding members in these sort of efforts, but here this is an exception where IIT Madras was involved right in the beginning. Right. So let's get into a little bit now. You understood sort of the technical stuff and how it involved. Now I'll switch gear a little bit into the India side of it and why should you care. I think there's a call. Let's take the call. Hello.
Hello. Hi, sir.
Hi. Please tell me.
Sir, I have a doubt, sir. How does RISC-V handle memory operations differently compared to CISC architectures?
So actually, if you see the overall flow, right, the way you, the way you do operation, the flow of the operation is the same. Initially, you load the entire program into the memory, and then you, whenever you want to execute, you move it to the registers on the chip, and then the ALU operates on the register. So that flow is the same whether it's a CISC, RISC, or any type of thing, right. This is called basic von Neumann architecture, and that has not changed. There are some new architectures which want to do things differently, but from an architectural perspective, that flow is the same, right. What is different is that generally the RISC has a lot more registers on the chip, compared to the CISC. So after they fetch from the memory, right, they typically want to do smaller operations, and lot more of the data is in the registers, so they make less trips to the memory, right, compared to the CISC architecture. That's a fundamental difference, right. Less trips to the memory, so that the whole operation runs faster. Because memory operation, whenever you want to fetch something from the memory, it's almost multi cycles. It's 10 to 100 cycles depending on the architecture. But register fetch is just one cycle. So the less memory operations you have, the more faster the program is. That's fundamentally what RISC tries to do. Okay. Okay. Then let's move to, okay, idantha baane undi, right? This is all technical side. What do we do, right? As an engineer, what does this mean to me? So I'll talk a little bit about the Indian semiconductor ecosystem, where we were, say, in 2015 time frame when this is all happening, and where we are now, and what does this mean to you as an engineer, right? If you're looking at the next 10-15 years, what does this all mean to me, right? Why should I care, right? Let's get into that, right? Okay. So as one more thing, right? Essentially, if you see the operating system side, Windows was ruling the roost for a long time, and then Linux came about, right? Linux was the open source alternative to Windows, and that gave freedom to a lot of developers, right? With Windows, Microsoft controlled the entire bottom layer, and you could only write applications on top of the operating system. If you wanted to do any innovation in the OS layer in Microsoft, you can't do it. Only Microsoft could do it, right? When Linux came about, that changed the paradigm, where if you wanted to actually do something in the operating system, in the kernel, or any of those other operations, you could do in Linux. You could contribute, right? So this RISC-V is essentially, if you can show the foil, the Linux movement for hardware, right? Because if you take x86, Intel controlled it. If you take ARM controlled it, right? So these are the two most popular instruction set architectures, and both of them are controlled by two companies. So if you had some ideas of innovating in the instruction set architecture space, you couldn't do it. With RISC-V now you have that opportunity. Right? Okay, then let's get back to India, right? So I said IIT Madras was one of the founding members, right? So in this time frame around 2014, 2015, if you see where the Indian semiconductor ecosystem is, right? And I'll split this into three different things. First thing is fabrication, right? If you see the fabrication scene in India, we just had one fabrication facility in India called SCL, Semiconductor Complex Limited in Chandigarh, right? And they were doing around 180 nanometers, right? That was the scene back there. And then if you see in sort of after you fabricate a chip, you need to do testing and assembly, right? You need to test it and assemble it with a package and all that. And if you see that, actually there was just one company which was doing a TESOL in India at the time, which was doing a little bit of the work, right? Just one company. Right? Then what about the design space in terms of designing these chips and all that stuff? There were companies, I mean, a lot of MNCs were there, right? I worked at Intel for a long time, and I moved to Intel India and Bangalore in 2011. And in Bangalore, there were a lot of other MNCs, right? AMD, Xilinx, NVIDIA, and even Hyderabad had a lot of companies, right? And there were a lot of design services companies, right? These MNCs use a lot of companies which were doing design services. When I say design services, they would give part of the work of the chip to these companies and say, okay, my chip has 10 different blocks, you do these 3 blocks, right? Essentially similar to how all these IT companies were doing software. Hey, there's this big software product, right? Somebody else was defining the product, but you're doing execution of small units in the software thing. Similar to that, they have design services companies. Right? If you actually wanted to start your own semiconductor product company, right, it was very tough in those days, partly for 2 reasons. One, capital was not available. but more importantly, if you want to design a product, you need to have a CPU in there. And the only option, there were other small companies, but the only option for companies was go to ARM and say, hey, can I license your ARM CPU, and then I'll design a product around it. And ARM didn't care, right? I talked around that time, I was actually at Intel trying to build a fabless ecosystem in India, and talked to quite a few people who were trying to get into the product space, and when they went to talk to ARM, ARM didn't care, right? India is too small a market. So beyond capital, they really didn't have the collateral necessary to actually design a product, right? So those are the three things. Remember these three things, right? Fabrication, assembly, and design. Then we'll see where we are today, right, and what changed. Right? Then the fourth thing more I want to emphasize is computer architecture, right? In this domain, what work was going on, right? There were other efforts going on, but this RISE lab and Shakti group at IIT Madras, right, that Professor Kamakoti was heading, Professor Kamakoti, who is currently the director of IIT Madras, he has been in the computer architecture domain for a long time, right? And then, right, he was the one heading that effort. Right? I think there's a question. Would like the question.
Hello.
Hello, Chappan sir.
Sir, ఫ్రెషర్ గా నేను ఎంబెడెడ్ డిజైనింగ్ సైడ్ చేయాలి అనుకుంటే ఎలాంటివి నేర్చుకుంటే బెస్ట్ అని నేను ఒక ఫ్రెషర్ గా నేను స్టార్ట్ చేయాలనుకుంటున్నాను సార్.
యా గుడ్ క్వశ్చన్. ఏ ఇయర్ మీరు ఇప్పుడు?
సార్ 2024 పాస్ అవుట్.
2024. ఏంటి మీ బ్రాంచ్ ఏంటి?
ఈసీ సార్, ఎలక్ట్రానిక్స్ అండ్ కమ్యూనికేషన్స్ ఇంజనీరింగ్.
గుడ్. మీరు ఏం నేర్చుకున్నారు మీ దాంట్లో? డిడ్ యూ లర్న్ కంప్యూటర్ ఆర్కిటెక్చర్ సైడ్ ఏం నేర్చుకున్నారు మీరు?
నార్మల్ గా అయితే మేము ఇన్స్టిట్యూట్ లో ట్రైనింగ్ తీసుకున్నాం సార్, సాఫ్ట్వేర్ సైడ్.
ఓకే, సాఫ్ట్వేర్ అంటే చిప్ డిజైన్ సైడా లేకపోతే వేరే ఎలాంటి సాఫ్ట్వేర్?
ఎంబెడెడ్ సైడ్ సార్, ఎంబెడెడ్ ప్రోగ్రామింగ్ సైడ్.
ఎంబెడెడ్ ప్రోగ్రామింగ్. సో యూ కెన్ డూ అసెంబ్లీ లాంగ్వేజ్ ప్రోగ్రామింగ్?
Yes sir, not an assembly language, so normally configuration type protocols.
Okay, good. So Balakrishna na? Okay. So
yes, sir.
So Balakrishna, meeru hold on to your question, right? Good question.
Okay.
I will address this down the line, right?
So, sir, here the problem is actually I done course at software side. So I got at embedded hardware designing side. So I have one doubt. For picking of the processor, what are the consideration factors for that?
Yeah,
I need to pick for that for the, suppose if I for example I need to look for it as at I think you know a flight attendant panel.
Yeah.
For that processor, I need to pick, sir, for first what are the factors I need to consider to pick the processor for that.
So Naka, I have a foil specifically for this. I'll address it, but I'll maybe I'll answer your question a little bit. Right now, if you see not just processor, if you're doing an embedded design, right? You need to pick probably you have around, I don't know, 5 to 6 different options in the market, right? There are a lot of ARM based chips available in the market, right? There is nowadays there is RISC-V based chips in the market, right? And then maybe some other proprietary architectures. Right? So as a embedded designer, I think maybe there are 3 or 4 considerations for you, right? First thing is technical consideration in terms of all the technical specs you have, right? In terms of what your product needs to do, right? The chips that you are looking at, right? I mean chips ante there are say from NXP oka chip untundi, right? Or Infineon oka chip untundi, right? Or there are bunch of Chinese companies and Taiwanese companies, right? So you are essentially looking at chips from these companies and trying to decide which one, right? And then that also has multiple architectures. One will have an ARM architecture, one will have a RISC-V architecture, the other one will have some other proprietary architecture, right? So for you as a as a designer of this embedded system, right, there are 3 or 4 considerations. First thing is technical considerations. Generally what happens is none of the chips exactly fit what you need, right. నీకు ఒక 10 స్పెసిఫికేషన్స్ ఉంటే ఆ చిప్ ఒక 8 స్పెసిఫికేషన్స్ సాటిస్ఫై చేస్తుంది, then 2 of them it doesn't. So you have to do something else, maybe use some other chip or some other means to do that, right. So you have to do the best fit technically, that's one. And number 2 is cost, right. Cost is always important, right. So beyond these 2, the third one is sort of ease of development, right. Ultimately ee rendu anta pedda decisions kaadu, because they are sort of black and white. Technical specifications either they meet or they not meet. Second one, in terms of cost, నీకు numbers ఉంటాయి, ఈ చిప్ ఇంత ఈ చిప్, that's also easier decision. The third one is the most important one, which is how will the customer support me, right. Because the real effort is once you start the development you will run into issues. Then in terms of the support, right, you will run into issues on the driver development, software stack development, lot of it. Avi resolve chesukodaniki how much of collateral is available, right, and if it's not available, that vendor of that chip has to support you, right. You run into some issues, maybe some driver needs to be revised, they need to help you, right. Our support system, right, enta bagundi anedi, that's what actually, that's where most of the people run into issues, not on the first 2, right. So that's where you have to spend some time looking at talking to other people who have used similar chips and see, right, enta time pattindi meeku develop chesukodaniki. Okay, so beyond this RISC-V specifically, if you are interested in this, I'll have a foil that I'll get into it, right. So this last one, right, foil low computer architecture, right. So this lab is important because this played a key role in RISC-V in India, and I want to get to that, right. So this is where things were in 2014, 2015, right. Then what happened was the Indian government, right, started something called IMDP, right, if you can show the foil. It's called India Microprocessor Development Program, right. So this was funded by MeitY, right, Ministry of Electronics and Technology, and the main aim was to have a family of microprocessors that are indigenous to India that we use on our own, right. Like I said, if you are a startup and you wanted to develop a product on your own, essentially ARM was the only choice, right. There was nothing in the country. There were actually efforts in the defense and ISRO, they have developed their own microprocessors, but that was just for them, right. There was nothing available for a commercial company, right. So Indian government started this program called IMDP, and they funded 3 institutes, right. The first one is IIT Madras, as I talked, because they had a really good program. The second one was a Center for Development of Advanced Computing, right, and the third one is IIT Bombay. So out of all these 3, right, there were products that came out. IIT Madras developed this thing called Shakti series of microprocessors, and CDAC developed these microprocessors called Vega series, and IIT Bombay went in a different route. I won't talk much about that because that is not based on RISC-V, because this session is for RISC-V. Both IIT Madras and CDAC, what they developed is based on RISC-V, right. IIT Madras, as I said, was a founding member of the RISC-V Foundation, right. So I'll talk more about those things, right. And the motivation, as I said, was 2 things for this entire program, right. To have a strategic autonomy for the country. As a country, India should have its own microprocessor so that they are not dependent, right. Not for everything, but at least when somebody wants to design their own, at least they have a choice, right. And then to spur the fabless ecosystem, right. One of the reasons the ecosystem was not growing was because, you know, the ARM and other companies, they didn't care about the Indian ecosystem. And then this whole program was branded as a Digital India RISC-V DIR-V program in 22, right. So right now you'll hear more DIR-V whenever you see these announcements and all that. So this happened around the same time, right. Then I'll talk a little bit about Shakti because I was very closely involved with this. I was at Intel at that time, and I worked very closely with these guys to actually realize their designs into silicon, right. If you can show the foil, there is a lot of effort that goes on in terms of designing, right. Designing is not that hard, but you need then actually to turn it into silicon, there's a lot of money that you need to spend. So that's where I work closely with the RISC lab at IIT Madras, and they actually taped out their design on Intel 22 nanometer process, and this is the first microprocessor actually that was completely designed in India, right, and proven on a 22 nanometer process, right. So that gave them a lot of confidence. And then subsequently they also actually put the same designs on the 180 nanometer process at SCL in India. That second one is called REMO. So that REMO can say actually a full made in India effort. It was completely designed in India and manufactured in India, right. And then subsequently they also taped out some of the smaller core, but these three, right, that you see on this foil, right, played a major in actually providing confidence to the team and to the rest of the folks in India that we can design our own microprocessors and fabricate them, and they worked really well, right. All three of them, they came out of the fab and we booted them up. Essentially one day Linux was up and running, right. So that was very good effort. So that sort of spurred the RISC-V ecosystem in India, and out of which this effort 4 startups came out of it. Right now there are 4 startups that are very actively working on RISC-V based stuff, out of which Mindgrow, Incore, Vyoma and Chakra, and I'll talk about one of it, right. So if you wanted to do a RISC-V based product today, right, say you're a young entrepreneur and you want to design a product, a chip, right. So there are 2 providers in India today, right, Incore and Vega. So Incore is a spin-off from this IIT Madras effort, and they do 2 things. First thing is obviously RISC-V cores, right, you can license a core from them. This is based off the Shakti. And the second thing they are working on is actually very interesting. They don't want to give you just a RISC-V core, right. They actually are working on a product called SOC generator, where you can give your spec to them saying that, hey, here is all the things I want in my SoC, the CPU, this peripheral, this input, this output, put it all on a spec. That is the input to their tool, and the tool generates most of the front end, right, the RTL for your SoC, and then you have to do some back end work, right. So they're trying to make the entire chip design process a lot more automated, right. So that's one thing. The second company is Vega. So this is a CDAC effort. Again, they have couple of cores that are available, and you can see the roadmap. They have more cores in the process. So today in India, if you want to design a RISC-V based product, right, you have these 2 options that you can license your core from. Okay, then let's see where we are today, right. So this effort all happened, and IIT Madras was was initially part of it, and we have few companies came out of that. And if you see today where we are in terms of the semiconductor ecosystem in India, by the way, before I get into all the companies, if you see the market today, right, 2024, the semiconductor market in India is around $40 billion, right, $41 billion, and it's projected to grow to $150 billion, right. This is all good news for all you guys, right. A lot of engineers are going to graduate, and we're going to have a lot of jobs to cater to this market, right. And then the government has been very focused on this Make in India, right. So what does Make in India translate for the semiconductor sector? So if you see Make in India, first one is fabbing in India, right, fabricating in India. So this is a strategic capability we need to have, right. If you're following the geopolitics today, TSMC, almost manufactures 60 to 70% of the chips in the world, and it's just based in Taiwan, most of their capability. They're building some new fabs in the US, and then there are few other fabs, Intel, Samsung, Global Foundries, right. But between US and Taiwan, there's a lot of it, and China is building a lot of stuff right now. So, and the relationship is not good among all these countries, right, and that will continue to be so. So, it's very important for us to have our own strategic capability, right. So, that's number one. We had this SCL for a long time, and the government is modernizing it right now, but we need to have some of the newer nodes that's still at 180 nanometer. It's older technology. That's number one, right. Number two, assembly in India, right. Like I said earlier, we had just one company, but this is something we need to have a lot more of, not just one company, right. And this can be done with less capex, right. Fab requires a lot of money, but assembly factories don't require that much money, right. So, fabrication, assembly, and then design in India, right. Again, designing in India is beyond foundation. It's a security capability, right. There are a lot of, if you see that $41 billion, all those chips we completely import them. They are not designed here. Okay, some of the our design services companies and MNCs might have done some part of the project here, but the IP is owned by somebody outside India, right. So, that entire solution is owned by somebody outside India, and then they are fabricated completely outside India, right. So, that $41 billion, right, there is a lot of it, and it is growing to $150 billion. If we do not do anything, that still will be completely dependent on the outside countries, right. So, that is where these three things, right. So, if we want to get a piece of that market, we need to take action in all the three areas: fabrication, assembly, and design. And design, not just design services, we need to build our own products. That is where the real value comes in, right. So, fortunately, right, the government has spent a lot of money and a lot of effort over the past 10 years, and we have a lot of efforts going on. So, if you see what is going on today in the fabrication space, right, beyond SCL, right, we have Tata and PSMC building a fab in Gujarat. This will have 5 different nodes from 90 nanometer to all the way to 22 nanometer. So, that is really good news, right. I mean, we do not really need the latest and greatest 2 nanometer, 3 nanometer, frankly, right. That takes a lot of around $5 to $10 billion, huge amount of money, right. We can't put that money, and we don't need that capability anyway. For most of the chips that ship today in the market, right, 80 to 90% are on the mature nodes, right, 22 nanometer and higher. So, what Tata is building can actually build a lot of products. Beyond Tata, there are other fabrication projects also. If you can show the foil, there are other fabrication projects also that are happening. There is a company called Third iTech, which is actually building a compound fab that will do CMOS sensors. If you see now, every phone has multiple cameras, and there are so many CMOS sensors that get shipped. So, this company is doing one of it. I think we have a question. Let's take the question before I move forward.
Yes. What are the advantages of RISC over CISC in modern computing?
Modern computing and in any computing, right? Essentially, two things. If you followed the earlier portion of the thing, right, it actually makes the hardware smaller in size, right, and the software gets a little bit more complicated, but the chips, RISC chips, are generally smaller. And when the chip is smaller, because like I explained, right, you can do more of the work using, it's a smaller set of instructions. So, generally, when you are doing a lot of complicated work on the chip, then the logic also to do that complicated work becomes bigger. So, the size of the chip also becomes bigger. So, generally, if you compare the CISC and RISC chips, the RISC chips are smaller. If they are smaller, that means the cost is lower, right. But consequently, the software is a little bit complicated, right. If you are reducing the complexity in the hardware, it has to go up somewhere else. It goes up in the software, but people have been okay with that, right. Fundamentally, that is a difference, right.
Okay.
But beyond, the question I think for you engineers is not, I would not say technical per se, right. Technically, there are differences. If I am an engineer, graduating now, this RISC-V, why do I care, right? I'll get to that, right? Why should you care, right? Yeah. Okay, so if you can show the foil, right? On the fab side, there are a lot of fabs coming up, right? Tata is the one that's getting built right now. Third High-Tech is building a CMOS fab. Tower Group and Adani Group are also planning to build, right? So this is fabulous news, right? Frankly, I've been in this industry for 30 years now, and I've been closely associated with a lot of efforts to build fabs in this country. I was at Intel, part of a lot of conversations. I never thought I would see this level of fabs in our country in my lifetime. So this is really good news, right? This gives our country a lot of strategic autonomy, right? Things could happen anytime between China, Taiwan, US, China, all those things. We need to have our own capability. That's number one. In terms of assembly and test, there are at least 5 different assembly and test factories coming up. Micron is building their own, Tata is building their own in Assam, Keynes and Renesas and Suchi are building in Gujarat, and in Hyderabad we have ASIP building soon, right? So this is really good news. We'll have our own assembly and test ecosystem. By the way, both this fab and assembly and test, this is not just one factory, right? When something like this comes, there is a whole ecosystem of vendors. They all come with them too, right? So recently I was at this ISA Vision Summit. ISA is India Electronics and Semiconductor Association, which is an organization of essentially all the semiconductor companies in India. They have this Vision Summit, annual Vision Summit. The last one was in February in Gujarat. Normally we used to have essentially Indian companies, but this one there are so many Taiwanese and Japanese companies who are suppliers, right? When you're putting up a factory, they supply all this test equipment, chemicals, substrate, lot of things. So they all come, right, and they establish entire ecosystem. So there are a lot more jobs created in this sector, right? So this is a big multiplier effect, right? So that's a fab and assembly. Beyond that, let's get to the design. I think for most of the audience today, that's the relevant part, right? So in design, right, the first bullet, I don't know how many of you are really familiar with this. 20% of the semiconductor design workforce of the world is in India today. So this is actually, a lot of people get shocked when they hear this number. If you see all these companies, right, MNCs, Intel, Nvidia, all these big companies, right, and then even the Indian companies in the design services space, right, L&T, Cyient, Wipro, all this. The number of VLSI design engineers across all these companies are 20% of the workforce across the world, right? So we have a huge ecosystem. That's really good, because I moved to India from China. So I was in US for a long time in Intel US. Then I was in Intel China for 4 years. Then I moved to Intel India. I moved here in 2011. Okay, and then I've been very closely associated with the Indian semiconductor ecosystem since then. And if you wanted to start a startup in this space, right, there were 3 issues at that time back in 2011. Number one was capital, like I said, right? Venture capitalists were not willing to fund. The situation has changed a bit now. Number 2, collateral was not there, whether it is the ARM was the only supplier. You didn't have anybody else to go to, and they were not willing to spend time with the Indian companies. And the third one was number of engineers who are proficient actually to design the chips, right? So if I see from then to now, right, all 3 of them, right, I don't have to worry. I really have to worry about what kind of product I want to build and how I'm going to win customers, right? There are enough venture capital companies willing to fund. Even government funding is there, called DLI scheme and PLI scheme, right? You can get 15 to 30 crores. Now with the RISC-V, you don't have to think about, I have to go beg ARM, right? By the way, ARM also, ever since RISC-V came into the picture, their lower end cores, they're essentially giving away for free. It's amazing what competition does, right? So there are RISC-V cores available. And then the third one, like I said, there are enough engineers who are proficient. I really don't have to worry about putting a team together, right? But there's still one significant challenge I'll get to, right? So bottom line, is a vibrant end-to-end ecosystem in semiconductor establishment underway, right, which is really good news for all the engineers who are about to graduate, will graduate in the next 10-15 years, right. if you ask me, this is really the start of the golden age for the semiconductor ecosystem in India. Right? A lot of people have been wanting to do this for last 10-15 years, but there were a lot of impediments. Finally, right, all of them got resolved. Now we're about to take off. Right? Now the question is, how can you be a part of it if you are a designer, right? So let's talk about design. If you can go to the foil. So the design part, right? So there are a lot of companies doing these design services, but what matters really is semiconductor products being done in India, right? Because unless you are building a product, you don't need a CPU core, right? If you are doing design services, ఎవరో డిఫైన్ చేస్తారు ప్రోడక్ట్, మీరు ఏదో చిన్న మాడ్యూల్ చేస్తారు, రైట్? యూ జస్ట్ నీడ్ టు యాక్సెస్ టూల్స్, సినాప్సిస్, cadence tools, and you do your own work. You don't need to worry about RISC-V, ARM, అవన్నీ ఎందుకు, right? If you are doing your own product, then it matters, right? So there are a few companies. I just want to, there are a lot more companies, by the way. There are around 100 plus startups, right? And in the product space, at least 20-25 companies which are designing their own products. I just picked a few just to illustrate the level of effort that's going on. So MindGrow is actually the one which is probably further ahead than anybody else. This came out of the Shakti effort, and they have built a secure IoT product, and right now they are pursuing customers, right? And the second one is called Big Endian, and they are building a CCTV SoC solution. If you see CCTVs today, they are everywhere, right? Actually, India is one of the biggest markets for CCTV, but guess what? All the chips in there, right, are completely Chinese chips, right? It's not complicated chip actually. It's we can design our own, right? But so far, like I said, for various reasons it didn't happen. But now we have startups designing. Right? This is also a security matter, right? Because it's CCTV and lot of it is sensitive installations. The government really wants to have Indian solutions, right? So that's one. Second one. And the third one is a company called Ahisa. They are designing GPON SoCs, right? Most of you guys have internet connections, and especially if you have a fiber coming in, right? Then you have this modem, fiber modem sitting in the thing, and there are lots of them, right? And these are all completely imported, by the way. There's no reason why you can't do it. So this company is doing it. And the last one is very interesting. Krutrim, Ola Krutrim. These guys are doing a very ambitious effort. They are trying to develop a AI solution similar to what NVIDIA provides, maybe not all of it, so that we will have our own equivalent solution. Right? So these guys are trailblazing this product space, right? And if you see the entire product building thing, right? If you are building a chip, any one of these chips actually, whether it's MindGrow, Big Endian, Ahisa, the chip they are building, the CPU, right? By the way, three of them, right? MindGrow is a RISC-V, Ahisa is a RISC-V, Krutrim is also RISC-V, although they don't publicly say it, and Big Endian is using ARM because they got a better commercial. The CPU is actually a small part of it. If you take the entire chip, right, maybe 10-20% of the area is occupied by the CPU. So the actual size on the cost on the SoC that the CPU is occupying is small, but it's very critical that you have control over it, because that dictates the access you have on the entire stack on top of it, right? So now if you want to get into the product space, right? So you have the sort of the choice to, with the RISC-V, to have your own design, right? Then what will you do with your own design? So this is where the critical part is, right? I think this couple of viewers asked, right? Which one is better? It's not technical capability that's really important. The key with RISC-V is the open part, right? If you can show the foil, right? If it's not open, then it doesn't really matter how technically better it is, right? So why is open important? And this is the reason why it took off, right? If you can show the foil, right? First thing, freedom for a fabless company. If you are starting a company, we have a RISC-V option right now, where you can license it from Indian companies, or there are a lot of foreign companies also, or you can, if you are good enough, the spec is open, you can design your own CPU, right? So that freedom you have, that's very important, right? Number one. Number two, I don't know if you can go full screen, right? ISA extensions, right? If you want to extend the instruction set architecture, right? This is you never had this option before, right? RISC-V defines a list of around some 30 to 40 instructions, right? That you have to implement, but beyond that, they give you the freedom to add your own instructions, right? A lot of people have good ideas of, hey, I want to be able to do this, right? But earlier you didn't have the choice, but now you have the choice. Like I said, similar to how you are able to do add your own stuff in Linux. Once Linux came, you could do innovation at the OS level that you couldn't do earlier. Similarly, with the RISC-V, you could extend the instructions and add your own innovations that you couldn't do earlier. Third one, security extensions. This is extremely important, right? With the RISC-V, you can add security instructions at the instruction level. Normally, security, what people do is they add some different modules and do something on software, right? There's a whole host of work. But with the RISC-V, you can extend it at the instruction level itself. You can do some security level stuff. But because it's open, you can do that, right? This is very important for a lot of government projects, right? That's the reason the government promoted this a lot, right? Because it's open and you can extend it. Security and extensions. High performance, right? If you look at ARM Neoverse, right? ARM did a lot of work. If you want to do a very high performance computer, right? For example, CDAC does some param level of high performance computers, right? ARM did a lot of work on their architecture so that it's easy for you to implement a high performance machine, right? Similarly, with the RISC-V, you can take it and then you can do all that work to do high performance machines. Accelerators, you can design your own accelerators. With the advent of AI now, there are a lot of people who are doing accelerators for very specific tasks, right? LLM is a good example. These large language models need specific instructions to be accelerated. So you can design your own accelerators, right? Okay, there's a call now. I'll take the call. And the last one, AI SoCs. Well, let's take the call.
Sir, good morning, sir. I'm Gladys from Secunderabad.
Hi, hello. Cheppandi.
Hello.
Yeah.
Sir, I have completed my BTech in CISC.
Okay.
If I need to start a career in semiconductor design, can you guide me and how to go forward?
Sure. So Gladys, what is your interest? Let me ask. Cut in, okay. Maybe she'll call back again. Gladys, please call back. This is an important conversation because in next fall, because this is actually the key question for all of you, right? How is this relevant for me? What can I do here, right? So this foil that you see right here, if you can go to the foil, these are all the things that let you that you can do with the RISC-V that you couldn't do earlier, right? So you have all these options, right? If you want to, if you are interested in this area, that's one thing first, right? Then you can do all these things, and there's a lot of scope to do all these things in the next 10-15 years, right? Especially the last one, AI SoCs. There are a lot of startups that some of my friends have started, ex-Intel and from other companies who are doing AI SoCs. AI is very broad term nowadays. So there's a lot of different kinds of products that you can build, and there's a lot of scope, right? For that, RISC-V is, because it's open, right? You can take it and then extend it, right? So I'll spend a little bit of time on one foil on RISC-V in China. This is important because they have really adopted it and they're doing a lot. Then I'll get to what Gladys was asking, right? What are the options for me, right? If I'm an engineer that is about to graduate or graduated or will graduate in the next 4 or 5 years, right? China sees RISC-V as part of this wider ambition, right? Please, if you can go to the foil. So I was in China for 3 years, from 2007 to 2010, and then China started putting a lot of money into their semiconductor ecosystem. Similar to what our government has done in the last 10 years, Chinese government has done it 15-20 years ago, right? But again, the US government had a lot of restrictions on what China could do. So this RISC-V, the Chinese government saw a big advantage, saying that, hey, x86 I don't have any access, ARM I don't have access, and they were trying to do their own things, but this RISC-V gave them an opportunity where they could adopt it and really sort of do their fabless ecosystem could grow a lot. So there's a very healthy ecosystem of RISC-V startups, 300 plus, right? Couple of my friends, my Chinese friends, they have their own startups, right? So I know there's a lot of work going on, and currently they are already shipping products in the low end segment, right? In that, I think one of the callers was asking about, hey, embedded domain lo chestunanu, right? What should I look at? And if you are in embedded domain, and if you look at what are the options, there are a lot of low cost Chinese products, right? Expressf is one company, if you are familiar. They have a lot of these low end microcontrollers, and most of them are based on RISC-V. Right? Earlier they were doing based on ARM and MIPS and other things, but they have switched a lot of it to RISC-V, right? And they are very cheap, right? They are not cheap because their costs are cheap, because they got a lot of back end subsidy from the Chinese government. That's a whole different subject, right? But they are already currently shipping RISC-V based low end products, right? So if you are designing something today, you can see them, right? And then they put significant investment in high end segment, right? Alibaba, Huawei, all these guys are designing server class products and this AI chips. So you can see the announcements almost right. The last 1 month there were a lot of announcements. You can just say RISC-V high end China in Google, you'll see a lot of this. And the RISC-V Foundation, which is actually it's based in Switzerland now, which sort of sets the specs and the future roadmap, and they have different class of members, and the premium members get a lot of the votes, and China has 13 out of the 25. Right? So they're taking a very active role in RISC-V development. It's an open standard, but open means anybody, whoever innovates, right, comes out on the top, and Chinese are putting a lot of money. So India needs to catch up, but good thing is it's an open standard, right? So ideas win, right? Whoever is more innovative, right, will win. Okay, now let's get to one of the key questions you have, right? Okay, all this is good. So what? What's in it for me? Fish or the foil, right? So again, on the left side, I'm showing this entire stack, right, starting from the very low end transistors, right, the physics of it, all the way up to the top where you talk about agentic AIs and LLMs and all that, right. The complexity goes up, complexity goes is low as you go higher, and the abstraction, right, is higher. And then on the right side, I show various kinds of jobs, right. So let's see at the very top, right. I mean, you hear this thing called prompt engineer, right. With all these tools today, right, all you need to do is the right level of prompts, and you get what you want. Coding, for example, earlier, people used to code, right, but nowadays, even in my own organization, right, people used to do Python coding. Okay, I want to do all these things. But nowadays with all these tools available, you just put, for example, in a Excel spreadsheet, here is the logic of what I want, and then you throw it into the tool generates all of it. So there is prompt engineering, right? That's one thing. I think a lot of that will happen. Then there is model developers, right? There's a lot of models being built, and lot of newer models coming, so there will be a lot of jobs in that area, right. There is model optimization. I know a lot of folks who are in this space, and this will continue to be, right. A lot of models get tweaked, right. There is new data coming in, you need to train the models and tweak the models, right. And there is high level language coding, whether it's Python or any other new languages, and there is low level language coding. When I say low language, like the C or any of these things, if you are an embedded engineer or a system level, right, you will do some of that. And if you come a little bit lower in the stack, right, at the system level, there is driver development, there is system integration effort, there is system architecture effort, right. So this is not supposed to be comprehensive. I just listed various typical jobs. And at the very low end, if you see, like say if you want to be involved in actually manufacturing these things, right, like say a Tata Fab, right, then the kind of skill sets you need there are more in the chemical engineering domain or the material science domain, right. I don't think we'll have a lot of those engineers in this call today. If you are, right, that's good then, because there's a lot of jobs, right, with these fabs coming in India, right. Then let's go to the one in the middle. This is where most of you will be, right. If you are a VLSI engineer, right, these four are probably where most of the jobs will be. In the front end, you will be either a design engineer or a validation engineer, or if we go a little bit towards the back end of the process, either a test engineer or the entire back end, right. Once you do RTL, you need to actually turn it into actually a layout and all that, right. This is where majority of the jobs are. But if you go up a little bit higher, these two, what I calling architect and micro architecture, right, this is where I see a lot of value being added in the next 10 years, right, and this is where RISC-V is relevant, right. With RISC-V being available right now, if you really want to do work in the instruction space, right, because now you can afford to, right, those are the jobs, right, as an architect and a micro architect, right, where you can add real value, right. This is not something you can just jump into. You can't become an architect, micro architect from day one, right. A lot of people who do this, they start out in this space where you actually do the design, because you need to understand the entire flow, right. You can't make decisions at the architecture level without understanding the implications of how it works at the logic level, how it works in the back end level. So you need to start at that level of designing the chip and or testing them, validation. You need to understand that entire flow, right, and then that helps you to grow to be an architect or a micro architect. And this where RISC-V really helps you to actually expand your space and have a lot more options, right. So to the bottom line, I think Gladys called. Maybe Gladys, you can call again and explain if you have more questions, or anybody else, right, because this is essentially the bottom line for most of you, right. Why does RISC-V matter, right? Because it lets you do a lot more things if you are passionate about this thing, right. If you are happy in this top, that's fine. A lot of you will be in this space, design and validation, that's fine. And then if you are really into chemical engineering and material science and work at the fab level, fabrication, that's good, that's great. But if you really are passionate about computer architecture and doing some fundamental contributions, with RISC-V you have an option today, right. Earlier with x86, no option. ARM, no option, because you can't touch the architecture, those companies control it. RISC-V being an open architecture and being widely adopted, right, so you have that option. So that's the really opportunity for you folks who are passionately interested, right, in working at that level. If there are any questions, we'll take. Otherwise, I'll just get to the summary. Okay, folks. Then let me just get to the key takeaways, right, of the session. Okay, first thing, right, what does RISC-V give, right? So I have three takeaways, right. First thing is this provides strategic autonomy for India in the semiconductor sector, right? Both from having options for our fabless ecosystem, right? So that we're not tied to any one company outside India. It's an open architecture, we can innovate. That's the first thing. Whether you want to extend the instructions or add your own instructions, all that stuff. Second one, this was a big accelerator for Indian startups. So like I said earlier, Indian startups, especially in the product space, right? They were just stuck with ARM, or there were a few other companies like MIPS and Synopsys had ARC compilers. There are other things, but most of them were proprietary, and you were at their mercy, right? If they were interested, yeah, they would. Otherwise, you didn't have a choice. But with the RISC-V, you're not at anybody's mercy, right? If you want a CPU, you're designing a product, there's an open source option. You can license from any one of these Indian companies, Inco or Vega, or there are a lot of foreign companies also, Sci-Fi, or if you have the talent yourself, you can design your own, right? Because RISC-V is an open standard, you can design your own CPU, right? So that's great, right? So it enabled and continues to enable the growth of the fabless ecosystem. And the third one, right? This is the one which is most relevant for you folks. This is a golden opportunity for all the VLSI engineers who are passionate about computer architecture to actually make impactful contributions, right? Earlier, even if you had the passion, you didn't have a platform. So RISC-V provides you that platform to do this thing. So so I hope out of all the engineers who are listening to this thing, at least some of you, right, are passionate enough to jump into this thing and make some really good contributions in this area, right, from our country, right? Because China is doing a lot, right, and US continues to contribute, but this is a good platform for India to do something, right? Okay, thank you, thanks a lot.